Have you ever stopped to think about how fundamentally digital our lives have become? From the moment we wake up and check our smartphones to the complex systems running global finance and healthcare, classical computers, with their simple on-off switches, their zeros and ones, have woven themselves into the very fabric of existence. It's been a revolution, no doubt. But what if I told you that revolution was just the opening act? What if the real technological earthquake is rumbling just beneath the surface, preparing to reshape everything we thought we knew about computation, security, health, and even reality itself? Buckle up, because we're not talking science fiction anymore. We're talking about quantum computing, and it's already here, quietly rewriting the rules of the game. Think back to 2019. While the world was going about its business, something extraordinary happened in a Google lab. Their quantum chip, named Sycamore, tackled a specific computational problem in just a few minutes. Why is that headline news? Because the most powerful classical supercomputers on Earth, behemoths costing millions and filling entire rooms, would have needed an estimated 10,000 years to arrive at the same solution. Let that sink in. Minutes versus millennia. That's not just an improvement. It's a fundamental shift in capability, a moment many are calling quantum supremacy. If you've heard the term quantum computing tossed around and maybe dismissed it as something only physicists in ivory towers care about, or perhaps a technology so far off it's irrelevant to your daily life, I urge you to reconsider. This isn't about some distant, hypothetical future. The shockwaves from quantum advancements are already beginning to propagate, and they're set to trigger tsunamis of disruption across industries we rely on every single day. From the security of your bank account and the development of life-saving medicines, to the intelligence of AI and the very way we discover new materials. In this journey together, we're going to unpack the fascinating, almost mystical principles that make quantum computers tick. We'll explore the specific industries standing on the verge of transformation, identify the global players locked in a high-stakes race for quantum dominance, and crucially, we'll confront the very real, very significant hurdles that still stand in the way. But stick with me, because we'll also uncover why these challenges, formidable as they are, likely won't stop quantum computing from hitting the mainstream much sooner than most people realize. Are you ready to glimpse the blueprint for the next decade, perhaps the next century? Are you curious about why understanding this now is not just interesting, but potentially crucial for navigating the future? Then, let's jump down the quantum rabbit hole together. Beyond zeros and ones, entering the quantum realm. All right, let's break down the magic without getting lost in complex equations. You know how traditional computers work, right? At their core, they rely on billions of tiny switches called transistors, representing information as bits. A bit is the simplest possible unit of information. It can be either a 0 off or a 1 on. Think of it like a light switch. It's either definitively off or definitively on. Clear, reliable, and the foundation of the entire digital age. It's served us incredibly well, powering everything from pocket calculators to planet-spanning networks. But it has inherent limitations when dealing with problems of immense complexity. Now enter the quantum world and meet the qubit. This is where classical intuition starts to bend. A qubit, the fundamental unit of quantum information, isn't restricted to being just a 0 or just a 1. Thanks to a bizarre but fundamental principle of quantum mechanics called superposition, a qubit can exist as a 0, a 1, or both simultaneously. Let's use that coin analogy again. In the classical world, you flip a coin, it spins, and it lands. Heads, let's call it 1, or tails, let's call it 0. The outcome is definite once it lands. Now, imagine the quantum coin. While it's spinning in the air before it lands, before you look at it to determine the outcome, it's in a state of superposition. It's effectively both heads and tails at the same time. It represents a probability of being heads and a probability of being tails. Only when you measure it, when you look at the quantum coin, does it collapse into a definite state, either heads or tails. Why is this simultaneous existence so powerful? Because it allows quantum computers to explore a vast number of possibilities at the same time. A classical computer with, say, 3 bits can only represent one of 2 3 equals 8 possible combinations, 0, 1, 10, etc., at any single moment. A quantum computer with 3 qubits, thanks to superposition, can simultaneously represent all 8 combinations. Now, imagine scaling this up. With just 300 qubits, a quantum computer could simultaneously explore more possibilities than there are atoms in the known universe. This exponential scaling and processing power is what gives quantum computers their almost unbelievable potential for tackling certain types of problems. But wait, there's another layer of quantum weirdness that adds even more power: entanglement. Einstein famously called it spooky action at a distance, and it's one of the most counterintuitive concepts in physics. When 2 or more qubits become entangled, their fates are inextricably linked, no matter how far apart they are separated. Measuring the state of one entangled qubit instantly influences the state of the other, regardless of the distance between them, whether it's millimeters or light years. Think of it like having 2 magical dice. You entangle them in a lab. You keep one die in New York and send the other to Tokyo. When you roll the die in New York and it lands on a 6, you instantly know, without any communication delay, that the die in Tokyo also landed on a 6, or whatever the correlated outcome is. It's not that information is traveling faster than light. It's that they share the same unified quantum state. This profound interconnectedness allows quantum computers to perform calculations where the parts are deeply correlated, enabling them to solve problems that rely on understanding complex relationships within massive datasets, something classical computers struggle with immensely. Now, harnessing these delicate quantum states is incredibly difficult. Qubits are fragile, prone to errors caused by the slightest disturbance. This noise has been a major bottleneck. However, recent breakthroughs, like those demonstrated by Google's Sycamore team and others, are showing that as they increase the number of qubits, they are also developing sophisticated error correction techniques. Think of it like having ways to constantly check and gently nudge the qubits back into their correct quantum states, filtering out the noise. These advancements are critical because they prove that scaling up isn't just adding more raw power. It's also about making that power more reliable and usable. This isn't science fiction speculation. The engineering is advancing, the error rates are dropping, and the race to build stable, powerful quantum machines is accelerating every day. The quantum shockwave, industries on the brink of transformation. So we have these incredibly powerful, albeit complex, machines founded on superposition and entanglement. Where does the rubber meet the road? Where will we first feel the impact of this paradigm shift? Don't expect quantum computers to replace your word processor anytime soon, but their influence is poised to fundamentally reshape some of the world's most critical industries. Let's start with cybersecurity. Right now, much of the world's sensitive data, your online banking passwords, corporate secrets, government communications, secure websites, HTTPS, is protected by encryption methods like RSA. These methods rely on the fact that it's incredibly difficult for classical computers to perform certain mathematical operations, specifically factoring large numbers into their prime components. A classical supercomputer might take thousands, even millions, of years to crack a strong RSA key. Enter the quantum computer. In 1994, mathematician Peter Shor developed Shor's algorithm, a quantum algorithm specifically designed to factor large numbers exponentially faster than any known classical algorithm. A sufficiently large and stable quantum computer running Shor's algorithm could potentially break current encryption standards, not in millennia, but perhaps in hours or days. This represents an existential threat to digital security as we know it. Imagine a world where all encrypted data suddenly becomes vulnerable. The good news: governments and cybersecurity experts are acutely aware of this threat. There's a global race underway, not just to build quantum computers, but also to develop quantum-resistant cryptography, QRC, new encryption methods believed to be secure against attacks from both classical and quantum computers. Organizations like NIST, the U.S. National Institute of Standards and Technology, are already standardizing these new algorithms. While the quantum apocalypse for encryption is likely still years away, requiring much larger, fault-tolerant quantum computers than currently exist, the transition to QRC needs to start now to protect data with long-term secrecy requirements. Think about medical records or national security secrets. They need to remain secure for decades. Next up, healthcare and drug discovery. Bringing a new drug to market is an incredibly long, expensive, and often frustrating process. It involves synthesizing and testing potentially millions of molecular compounds to find one that interacts with a biological target, like a virus or a cancer cell, in the desired way, without causing harmful side effects. This trial-and-error process can take over a decade and cost billions. Quantum computers offer a revolutionary alternative. Because quantum mechanics governs the behavior of molecules, quantum computers are uniquely suited to simulate molecular interactions with unprecedented accuracy. Imagine being able to model exactly how a potential drug molecule will bind to a protein in the body, predicting its effectiveness and potential toxicity before spending years and millions on lab experiments. This could dramatically accelerate the discovery of new treatments for diseases like Alzheimer's, cancer, Parkinson's, and countless others. It could lead to personalized medicine tailored to an individual's genetic makeup, or the design of entirely new enzymes for industrial processes. We aren't talking about overnight miracle cures, but quantum simulation can drastically shorten the crucial early-stage research phase, potentially shaving years off development timelines and bringing life-saving innovations to patients much faster. Think of the human impact: faster relief from suffering, extended lifespans, and cures for diseases currently deemed intractable. Now let's talk finance. The financial world runs on data, massive, complex, constantly changing datasets. Making sense of this data to predict market trends, assess investment risk, optimize portfolios, and detect fraudulent activity is a computationally intensive challenge. Even small improvements in accuracy or speed can translate into billions of dollars. Quantum algorithms, particularly those designed for optimization and machine learning, are perfectly suited for these tasks. Quantum computers could analyze market correlations and identify subtle patterns invisible to classical algorithms, leading to more accurate risk models and potentially higher investment returns. They could optimize complex portfolios with thousands of assets far more efficiently. Quantum machine learning could enhance fraud detection systems, identifying suspicious transactions with greater speed and precision. Major financial institutions like J.P. Morgan Chase, Goldman Sachs, and others are already actively experimenting with quantum algorithms, partnering with quantum computing companies to explore how these tools can provide a competitive edge. Imagine faster, more stable markets, more reliable financial advice, and significantly reduced financial crime. These are the potential quantum dividends in finance. And what about artificial intelligence, AI? Training today's large AI models, like the ones powering sophisticated language translation, image recognition, or complex scientific simulations, requires immense computational power and can take weeks or even months on clusters of classical computers. Quantum computing promises to supercharge AI development. Quantum algorithms could significantly accelerate the training process, allowing AI models to learn from larger datasets much faster. This could lead to more powerful, more accurate, and more nuanced AI systems. Imagine AI that can understand complex scientific research papers, assist doctors with intricate diagnoses, design novel engineering solutions, or even compose original music with greater sophistication. Quantum machine learning, QML, is a rapidly growing field exploring how quantum principles can enhance AI's capabilities, potentially unlocking new levels of intelligence and problem-solving ability across virtually every sector. Finally, consider materials science and energy. Discovering new materials with desirable properties, like lighter and stronger alloys for aerospace, more efficient catalysts for industrial processes, or materials that can conduct electricity with zero resistance, superconductors, at room temperature, is largely a process of experimentation and simulation. Classical computers struggle to accurately simulate the quantum behavior of electrons in complex molecules, limiting our ability to design materials from the ground up. Quantum computers, operating on the same quantum principles that govern matter itself, can simulate these interactions directly. This opens the door to designing revolutionary new materials with tailored properties. Imagine discovering materials that lead to dramatically better batteries for electric vehicles and grid storage, unlocking the potential of renewable energy. Picture the development of practical room temperature superconductors, which could revolutionize power transmission, transportation, think magnetic levitation trains, and medical imaging. Quantum simulations could help create more efficient solar cells or catalysts that convert sunlight and water into clean hydrogen fuel. The potential to accelerate innovation in sustainable technologies and address climate change is enormous. The common thread: quantum computing excels at tackling problems involving immense complexity, intricate systems, and underlying quantum phenomena. While many of these applications are still in their nascent stages, the groundwork is being laid, investments are pouring in, and the industries poised for disruption are taking notice. The potential isn't just incremental improvement, it's about unlocking entirely new possibilities. The new frontier: a global race for quantum supremacy. The race to build powerful, fault-tolerant quantum computers isn't just a friendly competition between tech companies. It's evolved into a high-stakes geopolitical contest, often compared to the 20th century space race. Nations around the world recognize that leadership in quantum technology could translate directly into significant economic advantages, national security superiority, and scientific prestige. Billions are being invested by governments and private entities alike, fueling intense research and development efforts. The United States is undoubtedly a major player, benefiting from a strong ecosystem of established tech giants and innovative startups. Companies like Google, IBM, and Microsoft are pouring vast resources into building different types of quantum hardware and software platforms. Google, as we mentioned, achieved a significant milestone in 2019 with its Sycamore processor, demonstrating quantum supremacy on a specific task, a symbolic, though debated, moment showcasing quantum potential. IBM has been particularly transparent, releasing a detailed public roadmap outlining its plans for scaling quantum processors, aiming for machines with thousands of qubits, and potentially achieving commercially viable, fault-tolerant quantum computing by the early 2030s. They've also made some of their smaller quantum processors available via the cloud, fostering a growing community of researchers and developers. Microsoft is focusing on a particularly challenging but potentially powerful approach based on topological qubits, alongside developing its Azure Quantum Cloud platform. However, China is mounting an incredibly ambitious and well-funded challenge. The Chinese government has designated quantum technology as a strategic national priority, investing tens of billions of dollars into research centers and initiatives. Chinese scientists have made remarkable progress, particularly in the field of quantum communication. In 2016, they launched the MISHA satellite, the world's first quantum communications satellite, successfully demonstrating secure quantum key distribution over distances exceeding 1,200 kilometers, a groundbreaking achievement that showcased their capabilities in quantum networking and cryptography. They are also aggressively pursuing various approaches to quantum computing hardware, including superconducting circuits and photonic systems. But the race isn't just a two-horse affair. Other nations are making significant contributions and strategic investments. Australia, for instance, recently announced a major $1 billion package aimed at developing its own quantum computer and fostering a domestic quantum industry, building on its existing strengths in quantum research, particularly silicon-based quantum computing. Canada, specifically the province of Quebec, with hubs like Sherbrooke, has emerged as a vibrant global center for quantum research and startups. It boasts a high concentration of academic talent and government support, fostering an innovative ecosystem that's attracting international investment and collaboration, positioning itself as a key player in the quantum landscape. European nations, through initiatives like the Quantum Flagship Program, are also pooling resources and coordinating efforts across the continent. This intense global competition revolves around achieving key milestones. Quantum supremacy, while perhaps more symbolic than immediately practical for all problems, represented crossing a crucial threshold, proving that quantum computers can outperform classical ones, at least for something. The next major goal is achieving fault-tolerant quantum computing, where errors can be effectively managed, allowing for complex, reliable calculations. The nation or corporation that reaches this milestone first could gain a significant strategic advantage. Imagine being the first to break current encryption standards or the first to discover revolutionary new drugs or materials. The implications for economic competitiveness, national security, and scientific leadership are profound, driving the urgency and investment we see today. It's a race where the finish line keeps moving, but the stakes couldn't be higher. Reality check: the towering challenges of the quantum world. Amidst all the excitement and futuristic projections, it's crucial to maintain a healthy dose of realism. Building and operating useful quantum computers is arguably one of the most significant scientific and engineering challenges humanity has ever undertaken. These machines are not just souped-up versions of your laptop. They operate on entirely different principles and face monumental obstacles. The single biggest hurdle is qubit stability, or rather, instability. Qubits are the heart of a quantum computer, but they are incredibly fragile. Their delicate quantum states, superposition and entanglement, are easily disrupted by the tiniest interactions with their environment: a stray vibration, a minor temperature fluctuation, electromagnetic noise. This phenomenon is called decoherence, where the qubit loses its quantumness and collapses into a classical state, corrupting the calculation. To combat decoherence, most leading quantum computing approaches, like superconducting circuits used by Google and IBM, require extreme operating conditions. We're talking about temperatures near absolute zero, minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, colder than the vacuum of outer space. Achieving and maintaining these cryogenic temperatures requires complex, bulky, and expensive refrigeration systems called dilution refrigerators. Even under these frigid conditions, qubits remain susceptible to errors. A tiny imperfection in manufacturing, a cosmic ray passing through, countless factors can cause a qubit to flip unexpectedly or lose its coherence. Developing robust quantum error correction codes is therefore essential, but these codes themselves require a large overhead of additional physical qubits to encode a single, more reliable, logical qubit, significantly increasing the scale required for fault-tolerant computation. Scaling these systems presents another monumental task. In classical computers, Moore's law described a relatively predictable path: cram more transistors onto a chip, get more power. With quantum computers, it's far more complex. Adding more qubits doesn't just increase power linearly, it increases the complexity of managing the system exponentially. Maintaining precise control and entanglement across hundreds or thousands of qubits, ensuring they all work together synchronously without interfering destructively with each other, is an immense engineering feat. It's not like stacking Lego blocks. Each added qubit introduces new potential pathways for errors and decoherence, requiring increasingly sophisticated control mechanisms and calibration. Imagine trying to conduct an orchestra where every musician is incredibly sensitive and prone to playing off-key at the slightest disturbance, and adding more musicians makes the task exponentially harder. Then there's the cost. Building a state-of-the-art quantum computer requires not just the specialized qubits themselves, but also the elaborate cryogenic cooling systems, precision microwave or laser control hardware, shielding against external interference, and highly specialized personnel. We're talking investments easily running into the tens or hundreds of millions of dollars per machine. Maintaining them is also incredibly expensive. This currently restricts cutting-edge quantum hardware development primarily to major tech corporations, well-funded government labs, and a handful of elite research institutions. Access for smaller companies, startups, unless they are quantum-focused, and most university researchers is often limited to cloud platforms offering access to smaller, non-fault-tolerant machines. This creates a potential accessibility gap and concentrates power in the hands of a few major players. Finally, even if we overcome the technical hurdles, identifying practical, large-scale applications where quantum computers offer a provable, significant advantage over the best classical methods is still an ongoing process. While we've discussed promising areas like drug discovery, materials science, and cryptography, many of the specific algorithms and their real-world implementations are still under development. Quantum computers are not general-purpose machines that will speed up every task. They excel at specific types of problems, demonstrating clear quantum advantage. Where a quantum computer solves a commercially relevant problem faster or better than any classical alternative, is the next critical milestone beyond the more academic quantum supremacy. Many current breakthroughs showcase potential and proof of concept, rather than immediate, deployable solutions ready to tackle industry-scale challenges today. That being said, progress is being made and it's accelerating. Google's Sycamore experiment, IBM's roadmap and increasingly powerful chips, breakthroughs in qubit coherence times, and advancements in error correction codes all demonstrate that these formidable challenges are being actively tackled. The path is steep, expensive, and fraught with difficulty, but the momentum is undeniable. We are steadily climbing the quantum mountain. Bridging the quantum divide, when does it touch your life? So, with all this potential and all these challenges, the billion-dollar question remains: when will quantum computing actually start impacting our everyday lives? The short answer is, not tomorrow in terms of having a quantum device on your desk, but its influence will likely start weaving into the fabric of industry and technology sooner than many people think. Most experts cautiously predict that we could see mainstream adoption in specific industries beginning in the early 2030s. This doesn't mean quantum laptops or smartphones replacing classical devices. Instead, it signifies a point where industries like pharmaceuticals, finance, logistics, and materials science will likely begin integrating quantum computing tools into their core workflows to solve problems that are currently intractable. However, we won't have to wait until the 2030s to see the first ripples. A crucial intermediate step, expected much sooner, is the rise of hybrid quantum classical computing models. Think of this as a tag-team approach. Complex problems will be broken down, with the parts best suited for quantum processing, like simulating a specific molecular interaction or running a complex optimization, being sent to a quantum processor, likely accessed via the cloud, while the rest of the workflow, data preparation, general calculations, user interface, continues to run on powerful classical computers. This hybrid approach allows businesses to start leveraging quantum advantages for specific, high-value tasks without needing fully mature, fault-tolerant quantum computers for the entire process. This pragmatic path significantly accelerates the adoption curve. We're already seeing the beginnings of this integration. As mentioned, financial markets are among the earliest explorers. Large banks and investment firms aren't waiting. They are actively hearing quantum experts, partnering with quantum hardware providers, and running experiments testing quantum algorithms for risk analysis, portfolio optimization, and algorithmic trading. The potential for even a slight edge in these competitive markets is a powerful motivator. Similarly, pharmaceutical companies are investing in understanding how quantum simulations can revolutionize their R&D. They are exploring partnerships and developing internal expertise to model molecular behavior, hoping to dramatically shorten the long and costly path to discovering new drugs and therapies. The potential payoff in terms of both profit and societal benefit is immense. The transition won't be like flipping a switch. It will be a gradual integration, starting with specialized applications in research-intensive and data-heavy industries. But the foundations are being laid right now. Companies are building quantum software libraries, developing quantum algorithms, training quantum workforces, and exploring use cases. As the hardware matures, error rates decrease and accessibility, likely via cloud platforms, improves, the pace of adoption will quicken. Quantum computing will move out of the exclusive realm of research labs and begin to deliver tangible results, shaping industrial capabilities and scientific discovery within the next decade. Why this quantum future matters to you. We've journeyed through the strange world of qubits, explored the industries on the cusp of transformation, witnessed the global race for dominance, and acknowledged the very real challenges ahead. You might still be thinking, okay, interesting stuff, but it sounds like it mainly affects big companies and scientists. Why should I personally care right now? Here's the crucial takeaway. Quantum computing isn't just another incremental tech upgrade. It represents a fundamental shift in computational power, a potential paradigm change akin to the invention of the transistor or the internet. And when a technology possesses that kind of transformative potential, its effects won't remain confined to niche applications or corporate boardrooms. Eventually, its ripples will spread outwards, touching virtually every aspect of society and consequently your life. Think about the impacts we've discussed. Your security. The race to develop quantum-resistant encryption directly impacts the future safety of your financial data, your online communications, and even national security infrastructure. Your health. Faster drug discovery and personalized medicine, enabled by quantum simulations, could lead to treatments for diseases affecting you or your loved ones. Your finances. More stable markets, better investment tools, and enhanced fraud protection could impact your savings and economic well-being. Your technology. More powerful AI, driven by quantum acceleration, could lead to smarter devices, more personalized services, and breakthroughs in fields we can't even imagine yet. Your world. Advances in materials science and energy, spurred by quantum design, could lead to cleaner energy solutions and more sustainable technologies, impacting the environment we all share. Staying informed about quantum computing isn't just about satisfying intellectual curiosity. It's about future-proofing yourself. Understanding the trajectory of this technology helps you anticipate the changes coming down the pike. New industries will be born, existing jobs will evolve, and entirely new skill sets will be in demand. Those who grasp the potential and the implications of quantum computing will be better positioned to navigate these shifts, whether as employees, investors, entrepreneurs, or simply informed citizens. We're already seeing startups in the quantum space attracting significant venture capital, signaling that investors believe this is not a fleeting trend, but a foundational technology for the future. Leaders in business and technology are strategizing around quantum's potential impact. Looking back at history, major technological shifts often seem abstract or irrelevant until they suddenly become ubiquitous. Think about the early internet or the first clunky mobile phones. It was hard for many to envision how deeply they would reshape communication, commerce, and daily life. Quantum computing feels similar now, complex, a bit esoteric, perhaps seemingly distant. The lesson here, for me at least, is the importance of staying curious and open to understanding forces that might initially seem outside our immediate sphere. Dismissing transformative technology because it's complex or not immediately applicable can leave us unprepared when its impact inevitably arrives. Engaging with these concepts, even at a high level, fosters adaptability, a crucial skill in a rapidly changing world. It encourages us to think critically about the future, to ask questions, and to consider both the incredible opportunities and the potential challenges ahead. The fundamental question isn't if quantum computing will reshape our world, but when and how. And as the pace of progress suggests, the answer to when might arrive much faster than many of us anticipate. Will we, as individuals and as a society, be ready to harness its power responsibly and navigate its complexities wisely? What are your thoughts? Which potential application of quantum computing excites or concerns you the most? Do you think the early 2030s timeline feels realistic, too optimistic, or too conservative? Share your perspective in the comments below. Let's continue the conversation. Thank you so much for joining me on this deep dive into the quantum realm. I hope this exploration has been insightful and sparked your curiosity. Wishing you all the very best of health and clarity in navigating the fascinating future ahead. And if you found this journey valuable and want to stay ahead of the curve on groundbreaking technologies shaping our world, please consider subscribing to the channel for more content like this. Your support helps us continue exploring these vital topics together.